Hey everyone, I want to continue our study of direct products of groups, and in particular, today I want to look at direct products of cyclic groups. And one of the questions that we want to ask or answer really is, when is the direct product of two cyclic groups cyclic? We saw a couple of examples last, I guess it was a couple lectures ago. Z2 cross Z3 we saw was isomorphic to Z6, so it definitely is cyclic. On the other hand, Z2 cross Z2, right, there's a direct product of cyclic groups that's not cyclic, right? So the answer so far is sometimes. So here's the question that we want to answer. So when is a direct product of cyclic groups cyclic? And to answer this question, we want to use one of the results that we developed, and this was, I'll just say recall, and I just want to paraphrase what theorem 11.1 tells us. What it tells us is that the order of an element GH is equal to the least common multiple of the individual orders, right? So this is happening in some, right? So this is happening in G cross H. So we'll need to use this fact in our study of direct products of cyclic groups. Now, one thing to be aware of, so let's say note that Z cross Z is not cyclic. And I mean, it's not, maybe not completely obvious, so let's talk about that. So the reason, and we'll go for a contradiction, I guess. So if Z cross Z was cyclic, then it would have to be equal to the cyclic subgroup generated by some element. In other words, it'd have to have a generator, and it would be a generator of the form A comma B. Then what would that tell us? Well, being a generator would have to give us every possible element in Z cross Z, so that would tell us then that 1, 1 is equal to K times AB, which is Ka comma Kb for some little k in Z, right? That's what it means to be a generator. In this context, because we're working with additive structure, that would mean that AB plus AB plus AB plus AB, some number of adding AB to itself would give us 1 comma 1. Okay, so that tells us that K times A has to equal 1 and K times B has to equal 1, which means, so then we would say, then K will have to equal plus or minus 1. Also, A will have to equal plus or minus 1, and B will have to equal plus or minus 1. That's the only way to get two integers to multiply out to give us 1. But then, okay, so fine. That would mean that we've got a plus or minus 1 here and a plus or minus 1 here. But then, one, 2 equal to M times AB is impossible. Because, oh, well, why is that? Because we have either a plus or minus 1 here and a plus or minus 1 here. All right? And then if we multiply by M to get 1 comma 2, that'll tell us that M has to be plus or minus 1. And then this is plus or minus 1 times plus or minus 1 is definitely not going to give us 2. All right? So this is impossible. Right, so we never could have had a generator A comma B in the first place. Okay, so now what we're going to do is consider the finite case. So we'll say, suppose G and H are finite cyclic groups. and let's give their I want to use some symbols for their orders. So let's say with orders M and N respectively. Right, so the order of capital G is equal to M, the order of capital H is equal to N. Now, if G, what do I want to say? If G cross H is cyclic, what would that mean? Well, it would mean that G cross H has a generator, right? And so, what would a generator look like? It would look like a little g, comma, little h. And the order of that element would have to be the order of the entire group, which is m times n. So if G cross H is cyclic, then there exists little g in capital G, little h in capital H, such that the order of that element, G comma H, is equal to M cross N. And so what does that tell us? Well, from the previous theorem then, we're going to need the least common multiple of those orders to be equal, or what do we need? We'll need, the least common multiple of the orders here to be equal to M times M. So by 11.1, we need least common multiple of the order of G and the order of H equal to M times M. Okay, so now let's actually just say what the answer is. All right, so what we need then is to know when this is going to occur. All right, if we have a group of order G, we've got a group of order H with orders M and N respectively, then when will we have a generator that satisfies this property? And so this is going to be theorem 11.3. So let's let G and H be finite cyclic groups. Then G cross H is cyclic if and only if the orders of G and H are relatively prime, and so let's write it like this. So if and only if the order of G and the order of H are relatively prime. So this situation is going to work out where we get an order, or where we get an element G comma H equal to the order, or whose order is equal to the order of the entire group, if and only if M and N are relatively prime. Okay, so let's consider the forward direction. So we're going to assume that G cross H is cyclic. So let's assume G cross H is cyclic, and let's write out our orders of our groups. So let's say, and let order of G equal M, order of H equal N. Since it's cyclic, we have a generator, so let's say also let little g comma little h in G cross H be a generator. So now let's let D be the GCD of M and N. And what do we need to do? Well, we need to conclude that D is equal to 1. So now let's say note that. So what I want to do is I'd like to raise the element GH to the order of mn divided by D. Now, okay, so let's break this out. So this is G raised to the mn over D, comma, H raised to the mn over D. And then if you fiddle around with this, so let's see, what do we get? We will get G to the m raised to the n over D, comma, H to the n raised to the m over D. From one of your homeworks that you just, I think you just turned it in today. You know that G, little g, raised to the order of capital G has to be the identity. Same thing here, H raised to the order of capital H has to be the identity. So what we get here is E, let's call it E sub G and little e sub H, right? So identity in G, comma, identity in H. Okay, so now that tells us, so what do we conclude here? So it follows that, well, let's see now. We know that the order of little g times little h, we know that the order is equal to m times n, right? Because g comma h is a generator. And then what did we just show? We showed that gh raised to this exponent right here has to be the identity. And so we know then that mn over d, this number right here, has to be greater than or equal to the order, because the order is the least exponent that gives us the identity when we put it up here. So now look at what we have. We have mn less than or equal to mn divided by some number d. That tells us then that this number d has to equal 1. Right? So therefore, d equals 1. All right, so that's kind of cool. Okay, so now we go in the reverse direction. I'm going to assume that the orders of G and H are relatively prime, and then we need to deduce that we've got a cyclic group. Okay, so in the reverse order, yeah, so let's do what we did before. So let's write the order of G equal to M, the order of H equal to N, and where we assume, so let's say we're assuming relatively prime now, so GCD of M and N is equal to 1. All right, so now we need to produce a generator, and the obvious choice is generator for capital G, comma, generator for capital H. So, so let's let G in capital G and little h in capital H be generators for remember, we're assuming that G and H were cyclic in the first place, so for the cyclic groups G and H respectively. So now, if we look at the order of the element G times H, remember what we're trying to do. We're trying to prove that G cross H is cyclic. In order to do that, we need to produce a generator, and that generator, or that element who's going to be a generator, will be a generator if and only if its order is equal to m times n. So I need to compute this right here. Now we know that this is the least common multiple of the order of G and the order of H. Oh, whoops. Yeah, which in this case we know is least common multiple. Which we know is least common multiple of M and N, right? Because little g is a generator, which means little g has to have order equal to the order of capital G. Same thing with little h. Now, the least common multiple of two relatively prime numbers is computed by just multiplying them. And so this is equal to M times N. That's what we need, right? So now we know that G cross H is a generator. So we can say, therefore, G cross H is equal to the cyclic subgroup generated by little g comma little h. All right, so that completes the proof. As a quick corollary, and this is just going to generalize it to more than two groups. So corollary 11.4, that says, all right, so a direct product of finite cyclic groups is cyclic. Oh, and I need to write out who these are. So direct product of finite cyclic groups, let's say product I equals 1 to n g sub I is cyclic if and only if the least common multiple of their orders is relatively prime for each pair, right? So if and only if, let's say, the order of gi and order of gj is relatively prime for each, or let's say whenever I not equal to j. In other words, we need our cyclic groups, the GIs, to have pairwise relatively prime orders. Right. Okay, and the proof of that is a straightforward induction, where the base case is the theorem that we just proved. Let's just end this with a couple of examples. So, for example, Z6 cross Z9. Well, the orders are 6 and 9, not relatively prime. This is not a cyclic group. So this is not cyclic. On the other hand, if we look at Z6 cross Z, what did I do here? 17. That's equal to, well, I shouldn't say equal, that's isomorphic to, right? 6 and 17 are relatively prime, which means that it's cyclic, and so it's going to be isomorphic to the cyclic group of order, it's 102. So it's isomorphic to Z102. And the proof of our theorem tells us how to find a generator. So a generator is any pair A comma B where A generates Z6 and B generates Z17. So think about who the generators of Z6 are. 1 minus 5. Oh, sorry, not minus 5. 1 and 5. And then remember, 17 is prime, so all non-zero elements of Z17 are generators, right? So take any such pair, and you've got a generator for Z6 cross Z17. Okay, so let's leave it off here. We do have an exam coming up on Friday. This is Monday's lecture, right? So yeah, there's an exam coming up on Friday. We will review for that on Thursday. And I think I'm just going to give you Tuesday off, right? So there won't be another lecture for Tuesday. It'll be more of like a catch-up day. We will see you. Well, I'll see you Tuesday in office hours, I guess, would be the next time. So if you're starting to get behind on any of this material, make sure to get caught up. Come see me in office hours, and we'll talk to you later.